Okay, welcome folks. I hope that you can hear me okay, and if there's difficulty with the sound, please let me know through the chat. Today's talk is on data visualization with R. I'm Rob Kabacoff, and I'm excited to be here today. Just a little bit about myself. I have been a data scientist for about 35 years. I've been teaching for about 10 years at the beginning of my career as a professor teaching statistics in a graduate school, and then 20 years doing data science consulting and the head of research for a international consulting organizational development firm. And then for the last 5 years, I've been professor of quantitative analysis at Wesleyan University in their Quantitative Analysis Center. I teach courses in machine learning, data science, and data journalism. And I'm the author of R in Action. And some of you may be familiar with the Quick R website. That's kind of where it all started. And I've been using R for about 15 years now. So I've got some experience I'd like to share with you. Just before we move on, I just want to point out a couple of things here. One is that, and this is of course the typical, comment that the material I'm going to talk about today comes from the 3rd edition of R in Action, which this is the discount code if you'd like to get it. And that all of the slides and the code and the data examples and also some additional resources I've put up on GitHub at github.com/rkabacoff/twitch. So if you'd like to follow along with the code, and if you want to run the code yourself, go to github.com to this URL and you can get the necessary files. Okay? I'm also going to put it in the chat so you can continue to see it. It's telling me that I can't chat, but hopefully you have this by now. Okay. So my expectation that most of you are pretty familiar with R, and but for those of you that are kind of coming in for the first time, just a quick update. R's language and statistical computing graphics platform, it's really based on the S language, which stood for statistics, that was developed at Bell Labs around 1976. And then 2 professors, Ross Ihaka and Robert Gentleman, decided to create an open source, freely available version of the S language in 1993, and its developments have led to what we have now. People ask where the R comes from in our language, and I don't know why Ross and Robert came up with it. My wife is convinced that it's named after me, and I'd appreciate if none of you would disavow her of that idea. So why use R? Well, it's free. And for those of you that pay monthly subscriptions to statistical packages, you'll really appreciate that it's open source, which means that you can see the code and you can change it. It's really got state-of-the-art graphics and data analysis, and it's the graphics we're going to talk about today. It's a very easy platform for developing new methods, and it runs on just about everything. It'll run on Windows, on Linux, on Mac OS X. I've seen instructions for how to install R on an iPhone. Depending on the kind of parties you go to, that might be cool, but I got to tell you that it's not really practical. And it has an enormous user base. What the enormous user base means is that there's a lot of people available to answer your questions. lot of the functionality in R comes from add-on modules called packages, which are collections of functions, data, and compiled code in a very, very specific format, which massively extends the functionality of R. And there are thousands and thousands of user-written packages on CRAN, the comprehensive R archive network that allows you to download and install these packages. And I checked last night, and there was 21,276 as of last night. I'm sure there's more today. When I get up in the morning, I have tea, I have cereal, and then I look at a website called Cranberries, which lists the new packages of the day, just looking to see what might be new and exciting. Both the upside of R is that it's changing so rapidly and it's expanding so quickly in its abilities to do things. The downside is that there's 10 ways to do any one thing in R, and there's a lot out there that, unless you're really looking at every day, you may be unaware of. So, as I said, there's a lot of ways to do things in R. And there's a lot of platforms, or not platforms, but systems within R for creating graphs. And we have base graphics, grid, lattice. You can do D3 graphics, which is basically JavaScript libraries using packages like R2D3. D3, if you're not familiar with, is very popular in things like data journalism. And what we're going to focus on today, which is ggplot 2, which stands for Grammar of Graphics, Plotting, version 2. I've never seen anybody that has ever seen version 1. If you want to create interactive graphs, graphs that you can interact with using a mouse, for example, mouse overs and brushing and connecting graphs together and that kind of thing. Leaflet for maps is very popular. Plotly is the other thing we'll talk a little bit about today. But there's also other packages for creating interactive graphs like RBouquet, RCharts, HighCharter. You can do interactive graphs with base using things like the identity function, but it is, identify function, but it's very limited. And you can use Shiny as basically a platform or a wrapper around creating interactive graphs. Here's a couple of examples, and if somebody could just send a chat to the chat box so I can make sure that I'm able to see any questions that might come up. I don't see any chat elements yet, so it'd be good if you have any. On the left, you see an example of a histogram. This is a data set of about 11,000 automobiles, and this is the distribution of miles per gallon for these automobiles. And it's very easy to run this function. It's just the hist function. It's very simple. It gives you a very simple graph. You can fancy it up a bit with base R functions, but you basically, that's what you get. On the right, you see an image of the distribution of miles per gallon using ggplot 2. And you can see that there's a histogram, and you can see a density curve, which basically you could think of as a smooth histogram. And you've got a jittered dot plot, where each point here represents a car. And if you do, you'll see that most of the cars have miles per gallon between about 7 miles per gallon and around, let's say about 25 to 30 miles per gallon, and then it starts to spread out. And you can also see that there's some clusters that appear after that. You get some cars with miles per gallon around 50 miles, get a few cars with miles per gallon around 100 miles per gallon, and even some cars around 125. Okay, I see a question. It's also very confusing. You look at solutions from Stack Overflow, you find many possible answers using many different packages. That's absolutely right. my suggestion and what we're going to focus in on today is one package. We're going to talk about ggplot, ggplot2. If you've never used ggplot, this shouldn't be difficult to understand. If you're a ggplot2 maven and you've used it a lot, I'm hoping to say some things that you haven't seen before. So hopefully you'll get some good things out of it as well. This graph on the right-hand side, made with ggplot2, I wrote a function called univariate plot, and that function basically wraps around ggplot functions and creates this graph. And I've put the code for this function up on the GitHub repository so you can see how it's made. And you can see that there's a lot more information in it. You can see that in the title it also has statistics about the distribution. There's down here there's also a box plot. We'll talk about that in a few minutes. Outliers represented as black points. And so you can get a lot out of this graph with ggplot2. One thing to make it better, to make it even a step up, is if you could mouse over it and move the mouse over a point and see what car, what make and model and year car it was. And we'll talk a little bit about how to do that later. Okay. Any questions so far before I start to launch into this? Okay, then let me move on. This is an example of an interactive graph. This is just an animated GIF right now. But you'll see that you can mouse over points and see information about those points. You can also zoom into areas of the graph and focus on that area and still be able to work with that area. And basically what we're looking at here is creating a graph with ggplot and then animating it and making it make it interactive with Plotly. We'll talk a little bit about that more later. For most of today, I'm going to use a data set that comes from the car data package that has to do with something that I care a great deal about: salaries for faculty members. And this data was collected in 2008, 2009 on 397 faculty members. And the concern that led to the creation of this data set was this university wanted to look at the question of whether or not there was gender bias in the salaries of male versus female faculty members. Okay, and so what they gathered was, and you can get this data by using this URL to get the CSV. So I'm getting the CSV, I'm signing it to the URL to an object, and then I'm reading that CSV file in and calling it salaries, and that's what we're going to work with for the rest of today. And it has information about the rank of the professor, assistant, associate, or full professor. Notice that it's listing it in alphabetical order, but assistant is lower than associate, is lower than full, so we're going to want to change that when we graph it. Their salary in dollars, whether they're a theoretical or applied discipline. We might think that people in an applied discipline are going to make more money than people in a theoretical discipline, or not, we'll see. Whether they're male or female, which is really the focus of gathering this data. This is also on GitHub, yes. And this URL actually points to that GitHub repository. I just thought I'd make it easy for you. How many years since they graduated, so how many years since they got their doctorate, and also how many years they've been in the field, years of service, because they may be a recent graduate, but they may have been working in a particular field for many years, and that can affect salary. And here is a screenshot of just the first few rows of the data set. And we're going to use different graphical techniques to look at this data. Okay. So, a grammar of graphics, that's what ggplot is. And in this grammar of graphics, we have to define the data. And the data has to be in the structure of a data frame. There's lots of ways of holding data in R. You can hold it as a vector, as a matrix, as a list, but it has to actually be a data frame to use with this particular package. And this is probably the most popular package for doing graphics now in R. And then a coordinate system. Everything we're going to do today is a 2D coordinate system. There's going to be an x-axis and a y-axis. If you were going to create maps, or you're going to look at pie charts, for example, you might use polar coordinates, map projections, but we're just going to stick with straight old 2D data frames. I mean, coordinate systems, but certainly ggplot can handle these other systems. Geomes. Geomes are the objects that we're going to place on our graph, whether that's points or lines or bars or error bars or bubbles, but any physical representation that we're going to stick on our graph, we're going to call those geomes, for geometric objects. And then the aesthetics are basically the mapping between characteristics of our data and visual aspects of our graph. So for example, we may make salary represented by the height on the y-axis and years of experience be the position on the the horizontal axis, x. And then we might, for example, say that the color of we may use points on our graph, and the color of those points will be mapped to whether the person is male or female. And the size of the points might be mapped to whether or not they're in an applied or a theoretical field. So aesthetics refer to the visual characteristics in the graph that are mapped specifically to variables in our data set. Now that's different than just assigning a value to an aspect of the graph, where I can make the points blue, but that's not an aesthetic. That's just a value that's assigned. An aesthetic refers to the link between a variable in our data and what you're seeing in the graph. And then scales. So for example, I might say, I want the size of a point to represent years of experience. Well, how are we going to create that? How are we going to relate the size of the point to the years of experience? What's that formula basically from going from years of experience to size of a point? And that's the scale. Most of this will be handled for you automatically. The stats, many of the aspects of graphs within ggplot involve different statistics that are coordinated. So you might add a trend line, a line of best fit, and that can get specified automatically. You could specify different kinds of statistics to graph. Facets are what Tufte calls small multiples. So let's say that I wanted to have a graph relating years of experience to salary, and I wanted to do it separately for males and females, but I wanted to do it in one graph, two graphs side by side. Those would be called facets. One of the things that what ggplot2 is so great at is creating these small multiples or facets, and we'll see that in a minute. So these are the things that make up the grammar of graphics, and the things we're going to be most concerned about are the data, the aesthetics, and the geomes. When we specify those, we'll get a nice graph, and then if we want to tweak it, we'll work with some of these other things. So let's just look at a simple graph. Now, how many assistant, associate, and full professors do we have in this data set? And so we start with the ggplot command, and we specify the data frame. What's holding our data? In this case, it's salaries. And then we specify an aesthetic. What do we want to have on our x-axis? And we're going to put rank. So we'll put assistant, associate, and full professor here. Okay, so we'll say x equals rank. And we could say y equals count, but that's really automatically assumed when you're creating a bar chart. If we had just said the ggplot, we'd have an empty graph, but now we specify that we want bars. And we use the geom bar function to do that, and that gives us our bar chart. And in ggplot, the default is kind of a gray background with white lines, but we're going to be able to change all of this, very easily. And notice that geom bar is a function, and as a function, it can take parameters itself. Some common parameters would be width, how wide do you want these bars to be? Fill, what color do you want these bars to be? So, and then color, the border around the bars. And then the position, we'll see examples of position in a minute. To use ggplot, it's really helpful to understand the difference between fill and color to ggplot. Color is the color for geometric objects that have no area. So a point, for example, theoretically has no area. A line has no area. The border around a bar has no area. So if I said color equals blue, I wouldn't get blue bars. I would get black bars that had a blue border around the edges. So whenever you see color in ggplot2, it's talking about lines, points, and borders. Fill is the color that you want for areas, like bars, like other things we'll see in a minute or two. So we could also, in our AES, I should have mentioned this, AES stands for aesthetic, and within the aesthetic function, this is where you put the link between your data and the aspects you can see. So here what we've said is we want to link rank to the x-axis. We don't have to specify the y-axis because it defaults for us, but we could specify the y-axis. And we ask for bars. Here we are linking rank to the x-axis. We're linking the color, the fill color of the bars, to gender, to sex. And we're asking for bars. And so adding this fill equals sex automatically gives us what's called a stacked bar chart. We can look at this and we can see, wow, this university has an awful lot of full professors. They have about equal amount of assistant and associate professors, and mainly they've got men. A few more women full professors than assistant or associate. If we use the position option, position specifies whether you want the bars to be stacked on top of each other, which is the default. So I could have said position equals stack, or position equals dodge, puts them side by side. Or what I think is very useful is position equals fill, which makes the height of each bar 100%. And this kind of graph, it's called a spinogram. Actually, it'd only be really technically a spinogram if I made the width relative to the number of faculty members, so if the widths of the bars were different. But basically, if we have a filled stacked bar chart, then it's a lot easier to see from this graph than from this graph that relative to the number of people within each rank, there's a lot fewer women full professors. Okay. That's bar charts. Let's go on to when you have a variable you want to look at that's quantitative instead of categorical. So if you have a quantitative variable like salary, for example, you could create a histogram. Again, the same ggplot statement. Again, we're mapping salary to the x-axis. Again, we don't have to specify the y-axis in this case because it's going to default to frequency count. And we ask for a histogram. And we'll get something that looks like this, and we can see, well, it looks like most of the faculty are making around 100,000. Some poor faculty are making around 50,000. And now we've got a couple faculty here that are making more than 200,000. So my first question is, who are these people and how come they're making so much more money than I am? some common options for the histogram function, geom histogram, would be the bin width. How wide are these bars? How many bars are there? The number of bins. The color, which again, remember, is the border, and then the fill, which is the color of these bars. If we wanted to, we could create frequency polygons. We just change geom histogram to geom freq polygon, and you could think basically of a frequency polygon as taking the midpoint at the top of each bar and just connecting them as a line. So a bit of a smoothed out histogram. Now and again, these are some of the common options. One of the nice things about frequency polygons is that when they overlap, they're still easy to read. So here's the frequency polygon for assistant, associate, and full professor. What I did was I created the width of the lines by saying size equals 2. The default is 1. And I map the color to the rank. It'll automatically give me a legend, and now I can see the spread here. Now, frequency polygons are okay, but I personally prefer to use density plots. So this is an example of a density plot, and you can think of it as a very smooth histogram. And we can see the shape of the distribution. All I'm doing is saying geom density, and I decided to fill it with red. And the way that you read this, you can look at this y-axis and you can go, what is this density? Well, think of it this way. The area under this curve is equal to 1. And if we want to know how many faculty are making between 150,000 and 250,000, we do a vertical line up from 150,000, a vertical line up from 200,000, and this area here between 150 and 200,000 is going to be some percentage of 1. And so the amount under the curve between 2 points is how many cases fall within that range. The common options, again, are fill and color, but also alpha. Alpha, which is available for all these geoms, is transparency, the degree of transparency. So if I want to plot a density plot for salaries for assistant, associate, full professor, and I don't want them to overlap so that I can't read them, I can make the alpha equal, say, 0.3. An alpha of 1 is perfectly opaque, which is the default. An alpha of 0 is perfectly transparent, so it doesn't show up on the graph. And 0.3 is pretty transparent. And now we can see some interesting things about this. We can see, first of all, that salary tends to go up as you go from assistant to associate to full professor. Clearly, associate professors are not making as much as everybody else. But there are quite a few associate professors that are making less money than assistant professors. You can see that overlap there. And there's a tremendous spread in salaries for full professor. Some full professors are making a lot, and some full professors are making quite a little. So that's something we're going to want to investigate. This is called the kernel density plot for multiple groups, and I find it very useful for comparing groups on a quantitative outcome. Probably more well known than a density chart is a box plot. Box plots are a way of describing the distribution of a quantitative variable. And we just change it to geom box plot here. Now here we do have to specify the y value. We didn't have to on the density. But from this point on, we're going to be specifying the y value. We want the rank to be mapped to the x-axis. We want salary to be mapped to the y-axis. And we want box plots. And in a box plot, the center dark line is the median for that group. The upper line in the box is the 75th percentile. The lower line in the box is the 25th percentile. And you've got 50% of the data within the box. these hinges, or these lines that are coming off the top and the bottom of the box plot, capture basically in a normal distribution will capture about 99% of the data. And so any points that are outside of these lines represent outliers. And so we've got 3 faculty members that are full professors. They're making way more than you'd expect, or way more than everybody else. And you probably want to ask why. My guess is they work in the medical school or something, or have big grants or something like that. The width of the box plot has no impact. It doesn't mean anything, which means that you can get a lot of box plots in a single graph. If you wanted to compare the distribution of 10 different groups on some outcome, you could easily put that into a graph and not worry about the graph getting too busy. Okay. A strip plot is basically a scatter plot. So here we're mapping salary to the x-axis and rank to the y-axis. And we can see each point represents a faculty member. And we can see the distribution of points in this strip plot. We ask for geom point to see the plot points. And they're in straight lines because, it's really just a categorical variable over here on the y-axis. And there's a lot of overlap. So we don't really know how many faculty are represented in this dark patch here. We can change the color and the transparency, and we can change the shape of the points, which we'll see in a couple minutes, the size of the points. And we can also jitter. This is a bit easier to see the distribution. So what is jittering? Jitter adds a random value to the y-axis, a small random value. Remember, the y doesn't really mean anything, because full professors are up here, associate professors are in the middle, assistant professors are down below. But other than that, y doesn't mean anything. And so adding a little randomness makes it easier to see the points that are overlapping, and we can see the spread of the data. And this would even be a little bit cleaner and easier to see if we made professor points red and associate professor blue and assistant professor green, and then this would be really easy to see. And to do that, we would just add color equals rank here in the aesthetic. Okay. Questions so far? Please be sure to put it into the chat. I'm used to teaching on Zoom, and it's a little bit odd not seeing you, but we'll keep going. Scatterplot. We're starting with a data set. Let's look at the relationship between years of experience and salary. So we'll put years of experience on the x-axis, salary on the y-axis, and we'll ask for points, and we can see that basically it looks like the more time you've been out since you graduated, the more money that you make. But then down here, once you've been out of school for about 40 years, which would be me, salaries tend to go down. So we're going to want to ask why that is. And things you can change are things we've seen before. I mentioned that you could change these are just filled circles for the points, but we could change that to any shape we want by specifying a number to represent a different shape. We can also add lines of best fit. So here's the relationship between years of experience and salary, but we've added in a smoothed curve. This is a low S curve. It's a non-parametric line of best fit. Basically, think about taking small sections of the graph and drawing straight lines within those sections and then smoothing it out. And the default is this smoothed line, and the smooth line is the blue line, and then the gray portion is a 95% confidence interval. And so we can see that the relationship between years of experience and salary really isn't linear. It's not just that the longer you've been out of school, the more money you make, but it really tends to go down after you've been out of school for a while. Now, I would argue, and I don't know this for a fact, that what we're seeing is that people that were hired a long time ago were hired at a particular salary, and they may get a cost of living increase every year. But if their duties haven't changed, you don't see big jumps in their salary. You usually get a big jump in your salary when what you're doing changes in a job. And so the people that were hired a long time ago got increments from when they were hired, but it really isn't the same as people that are being hired these days, where they're getting paid a lot more. That's just my guess about what's going on. If we wanted to use a straight line of best fit, we could specify the method. LM stands for linear model, or basically linear regression. And then we could specify a formula. Here we're specifying a linear line. Y is a function of x. Now the y and the x have nothing to do with variables that are in the data set. They just represent the y and x axis. So we could do y plus x. Y is a function of x and x squared, x plus x cubed. So basically, if we said poly x comma 2, that would give us a quadratic fit, a line with one bend in it. And we could say poly 3, which would give us a line with two bends in it, etc. So the next thing to talk about in understanding ggplot is grouping. And in grouping, what happens is you're representing several groups in one graph, and you're distinguishing among the groups by some aspect of that graph, such as color, shape, size, or transparency. So for example, here, this is grouping. We're doing years of experience by salary, and we're specifying that the rank should be rated to the color of the point, and it picks these colors by default, and we're asking for points. And that would be grouping. The alternative would be creating 3 side-by-side graphs, one for assistant, one for associate, and one for full professors. Here is an example of grouping where we're using both color and shape to distinguish the groups. Notice that when we said color equals rank, we got blue, green, and red for rank, and we got, it's hard to see, but that's circles and triangles for males and females. I don't recommend this kind of graph. That's kind of hard to read by shape, at least with points this size. If we were to do both color and shape as the rank, we'll get a collapse of, we won't get 2 separate legends. So ggplot will try to collapse the legends as much as possible. So now we have different colors and shapes to represent rank. Facets are where you represent the results of different groups as small graphs that are lined up in some kind of matrix. So, as an example, here is the relationship of years of experience and salary for females versus males. And the way we get this is with the facet grid function. So everything's the same, but we add facet grid, and we specify period tilde sex. This is rows tilde columns. Well, since we're not adding any rows, we just use a period as a placeholder, and we get a column for males and a column for females. If I had said sex tilde period, I would get a graph for males on top, and a graph for females on top, and a graph for males below. And if we specify both, for example, here's the plot of years since PhD and salary. Separate, we've got males and females representing rows, and we've got assistant, associate, and full professors representing the columns. And so we get a grid of a 3 by 2. 2 by 3, sorry, rows by columns. Okay. Up until now, we have put all of the aesthetics. This is one of those things where if you're really familiar with ggplot, I'm hoping this might be a little bit new to you. Up until now, we've been putting all the aesthetics in the AES function within ggplot. And when you do that, those aesthetics, those mappings, will cascade down to all the geoms. And so here I said color equals sex within the AES. And so I get different colored points. And I get a separate line for females and a separate line for males. One blue, one red. Okay. This SE equals false says I don't want confidence intervals. So sometimes that's easier to read. And so we can look at this and we can say, well, it looks like the relationship between time out of school and the salary that women get is even stronger than it is for males. But not that much stronger, so we'd have to take a look at that. Also, it's pretty obvious that women have not been in senior roles as long as men have been, because the female points end around 40 years and the male points keep going. But we can also put aesthetics within individual geoms. So I've moved the aesthetic of color mapped to sex to the point geom point function and not in the ggplot. And what that gives me is separate colors for males and females in terms of their points, but a single line of best fit for all the points for the smooth. So if I do this, the aesthetic only applies to the function that it's putting. So that's the difference between putting an aesthetic in the ggplot function versus putting it in within the geom function. Okay. So these are all the different geoms that you can add to a plot, and it gives you a tremendous amount of variability in terms of, and breadth in terms of the kinds of graphs you can make. We'll see a couple of examples going forward. Line charts, we would use geom line. This is a different data set that's just built into R that looks at unemployment by time. These are the different kinds of lines you can ask for. And so, for example, we can say, give me a dotted blue line that's size 1. And this graph is proof that I have absolutely no aesthetic sense whatsoever. But it does give you a lot of control over the way your graphs look. We haven't talked yet about scales. Scales are how the mapping occurs in the aesthetics. And if we want to change the X and Y axis, we can use scale underscore X continuous or scale underscore Y continuous. If it's a continuous axis like years of experience or salary, we can use scale underscore X discrete or underscore Y discrete. If it's a categorical variable like rank or sex. And we can do the same thing if we want to change the color mapping. So if we want to specify specific colors, I'll show you an example in a minute. Or if we want to specify fill colors as opposed to line colors, we could also do the same thing for shape and size. So here's an example. If I want to control the X and Y axis specifically, rather than use the defaults that come with ggplot, I can specify. This is the MT cars data set. I've left the salaries data set for a minute. MT cars describes the properties of 32 automobiles in 1973. And we're looking at the relationship between weight and miles per gallon. We can see that as cars get heavier, their mileage goes down. But we want to specify exactly what's on the X and Y axis. So here we say, give me a break from 1 to 6 every one place. So it gives me 1, 2, 3, 4, 5, 6. On the y-axis, give me a break from 5 to 35 every 5. And we can also specify the limits. 6 is the highest, 1 is the lowest, and 5 is the lowest, 35 is the highest. If you want to just look at a portion of the graph. We can do the same thing for scales with a discrete axis. So here, for example, we could use limits. And we can say for the x-axis, which is professor, assistant professor, associate professor, we can specify the order. So here we've specified the order as professor first, assistant professor next, associate professor third. Normally we would get it in an alphabetical order for a categorical variable, but now we're controlling the order. And we can also add labels to the scale function. So here I'm changing the word prof to full professor, and I'm using \n to give me a line break, assistant professor and associate professor. So one of the questions that come up a lot with ggplot is, how do I change the order of my bars? And you can do it with the scale discrete function. Colors are picked off of a color wheel automatically by ggplot. So if I'm going to try 5 colors, it's automatically going to pick the 5 colors on the color wheel that are as far apart as possible. You may or might not like those colors, so you can add your own. This again proves I have no aesthetic taste. Here I'm using the scale fill function. Manual, meaning that I'm going to specify the values myself. Red, green, and blue. Now luckily, R also provides, and ggplot provides, pre-made palettes with people that are a lot better at colors than I am. One of the most popular is the Brewer package. And so these are different color palettes you can choose. And this will be built into ggplot too. And so, for example, I can say the default is this color palette, light blue to dark blue. And I'm adding the function scale fill brewer to specify that I want to pick a palette from the Brewer package. Or I can specify a particular palette. This is the set 1 palette. And it gives me these colors. Set 2, set 3, set 4 give me other palette choices. We can pick the one that we like. So that's colors, but often when we create graphs, we also want to control annotations. The most common annotations are labels, and so we use the lab function. We add labs. And here I've given a title, relationship of auto weight to mileage. I've given a subtitle, which will appear here. I've given a caption, which will appear down at the bottom. A caption is usually the source of the data. I've changed the label on the X and Y axis. And if I specify a property that's being used for the legend, in this case, color is being used for the legend, I can say whatever I want as the title of the legend. Now notice here that I'm saving the results of this graph and I'm calling it P. In ggplot, you're outputting an object that can be saved and continue to be manipulated on. That's really nice, that you can create an object, a graph as an object, and save it and continue. I could change the label or labels without changing the graph. I can change the colors without having to recreate the graph. I can store the graph as an object and pull it back to work on later if it's a complicated graph. I can add lines and labels within the graph. So here I've added a horizontal line at 20, which is the average mileage, and I've added the words average mileage as a text annotation. You can change the overall look and feel of a graph with themes. Themes control things like the color of the lines, the color of the background, the fonts that are used in a graph. So for example, instead of a graph that looks gray with white lines, I could use theme_BW. Here I've just saved my graph and just added theme_BW. I get a completely different look and feel. There's lots of prepackaged looks and feels for graphs in the GG Themes package, including ones that are specifically designed for different journals and magazines. Here's an example of a prepackaged theme for 538. So this is the exact same graph as this, just with a different theme. Here is the same graph, but with the economist theme. You can get fancy. Here is a jittered scatterplot where I've added median lines and used, I forget whose theme this is. Here is an example of the relationship between years of experience and salary separately for male, female, separately for assistant, associate, and full professors. I see that I've only got about 10 minutes, so I'm going to shift focus a little bit here. Again, this is things I hope that may be new to some of you. You can easily combine graphs, and there's several packages in R that let you combine graphs. What you do is you create several ggplot graphs, and then you arrange them into a final graph. As I said, there are several packages to do that. My favorite right now is Patchwork. So the first thing I've done is I've used the set theme function to give me a minimal theme. And so for all the graphs that I create for the rest of my session, I'm going to have this minimal looking theme. Then I create separate graphs. This one of log salary, years of service, these are histograms. Here's a bar chart for rank, and then a plot of years of service versus salary. So here are my 4 graphs. Then I save them as objects. I use library patchwork, and then I say, give me 3 in the first row and the 4th in the second row. And then make the second row 3 times larger. Well, actually, think of it as there actually being 4 rows, and the first take up the first row, and the second graph takes up the second, third, and fourth row. So this graph is going to be much bigger than these graphs. And I've added, using plot annotation, a title and a subtitle to the entire new graph. And I could save that and save that as an object and continue working on it. So you can do a lot of really nice looking things combining graphs. And you could create a function that wraps around this to be able to use it if you're doing these kinds of graphs a lot. This is how I created that univariate plot graph. Okay, saving your work is easy to do through the interface. You can just click on the save button and then choose what you want it to do, or you can do it programmatically. And programmatically you use ggsave, and depending on the file extension will describe what kind of graph you're saving. So if it's a PostScript file, you'd do .ps. If it's JPEG, .jpeg, etc. The thing that I would be careful about, though, is that right now, Microsoft Office, if you save your file as a WMF, a Windows Meta file, that's what you would normally save if you were going to paste a graphic into PowerPoint or Microsoft Office, Microsoft Word. But if you do that with your WMF, you're going to lose any transparencies that you specified. It'll be as if transparency equals 1. And so it's better if you have transparencies to save your image as a bitmap. Save it as a JPEG, for example, or a PNG, and then paste it into Word or paste it into PowerPoint. In the couple minutes we have left, let me just talk a little bit about creating interactive graphs. It's actually pretty easy. You just create your graph using ggplot, and then you save that graph as an object, and then you run it through the ggplotly function. And that will create an interactive graph. If you want to control the tooltip, what shows up in a box when you mouse over some aspect of your graph, then you can add a tooltip option to the ggplotly function. So here I'm creating a new variable called auto, which contains the names of the cars, and I'm adding text equals auto as an automobile to my AES. And then I'm including in my tooltip X, Y, and the text variable. And now when I create this interactive graph and I mouse over it, we'll be able to see pop-ups that show what that point represents, and we can save it and put it into an HTML file. It'll save as JavaScript, and you can stick it into a web page. Some resources that I want you to know about, obviously, are in action. Everything that I talked about today is in that book and more. I've also, this is the Quick R website. That's what got me started in R. But I've also put up a site called Data Visualization with R that goes into a great deal of detail about doing data visualization with R. So for example, if you wanted to do other kinds of graphs we haven't talked about, like waterfall charts, for example, or word clouds, or correlation plots, or heat maps, or flow diagrams. Basically, I've put all of that onto this website. A lot of this will end up in R in Action, but not all of it. And so this is freely available. So those are the first two. Hadley Wickham wrote the book, obviously, on ggplot2, since he's the author of the package. And you can go to this website to see that online book. And Winston Chang has a very nice book on creating graphs with his R cookbook. And that is everything that I planned for today. So let me just open it up to any questions you might have. Okay, great. Vector graphic plots. Good question. If you want to create vector graphic plots, save your plot as an SVG, and it'll be a vector graphic. And then you'll be able to continue to edit it using either Adobe Illustrator or the free vector graphics editor. I like Inkscape a lot. What's the most important changes in the new Booker edition? That's a great question. So that's about R in Action 3rd edition. I had to rewrite R in Action because the way R is being used has changed a lot in the last 5 years. A lot more emphasis on tidyverse, a lot more emphasis on dplyr, tidyr, ggplot. So I've changed all the graphics from base graphics to ggplot in the book, including adding new advanced chapters on ggplot. There's new material on machine learning because machine learning's changed a lot, and I've learned a lot more about machine learning in the last 5 years. And so the book on the chapters on cluster analysis, the chapters on machine learning like random forest and decision trees. I'm not sure yet, add a section on gradient boosted machines, gradient boosted trees. I probably will take out the section on Rattle, because Rattle as a package isn't being used as much. And so basically, a lot more on pipes and the tidyverse and what's really been changing in graphics. Okay. I'm open to any other questions. Oh, great. Thank you. Oh, thanks for putting the link up there. Remember that all these slides are available on the GitHub. Okay, I'll stick around for a couple minutes if there's any other questions. If not, have a great night or day, depending on what part of the world you're in. Do I use Python? I'm learning Python. I'm not a good Python user yet. One of the issues for learning Python for me is I know R so well that there's crosstalk. There's, for example, a data frame, or a list in Python is not the same thing as it is in R. And so it's always been a question for me of, do I become more of an expert in R or do I generalize? Now, I teach several courses in machine learning, so I'm really going to have to get better at Python. But I don't do huge data sets. A few million cases is as large as my data gets. I don't deal in billions or trillions of rows of data, which is when I would really start to move towards Python. Great. Anything else? Okay. Thank you very much. I hope to see you again sometime.